All right, what's up, everybody? It's what is it? Wednesday. What's up, Mistral? What's up, Asta? Good to see you too. Yes, I'll explain that, Sib. Yeah, so it's not very well published. I had to like go digging around to find some random PDF that UCLA posted at some point, which actually detailed out the summer deadlines. So yeah, I found out I do get a little bit more time to grade than I thought, which is the next session starts like the next Monday. So I thought they needed everything wrapped by then. Turns out we have a couple more days. So as a result, I'm not going to make regrades for exam 2 due until after the final. So if you're studying for the final right now, don't worry about your exam 2 regrades. You don't need to get that all written up just right now. You can do it after the final. We'll have that due Sunday night. I just sent out an announcement like 5 minutes ago. But yeah, I'll reiterate some of it here. But yeah, regrades for exam 2 will be due Sunday night. Albert posted solutions, so you should see let me make sure those are public, actually. Sorry, let me make sure those are public. Sometimes when I upload things, they don't make them public to you guys to start with, which is super annoying. Yeah, no, good. Okay, solution guide. So that is public. Okay. Let me make this clicker question section public too. Okay, cool. So, yeah, regrades for exam 2 due Sunday night. You can start doing them now if you want. It's a good idea to go over what you got wrong on exam 2 anyways to help prepare for the final. But in terms of like writing everything up, you don't need to do that until Sunday midnight. But do it sooner than later if you want. It'll help ensure you hit the deadline for that. In terms of regrades for the final, I haven't determined that yet. It depends how long it takes for us to grade the final exam. So the final exam will be Friday. I'm giving a extended 6.5 hour window for it compared to the regular 3 hour window that the registrar wanted me to give. So should be a decent amount of time to do it. It's going to be about I'm working on writing it now. This is such a fast class, but by Thursday, I should have like a final outline for what the structure of it will be. But in general, I'm shooting for it to be around 1 to 1.5 times the length of a midterm. Yeah, so 1.5 is like, yeah, so think about instead of 4 multiple choice, there's 6. Instead of 4 free responses, there's 6. Instead of 2 scaffolding questions, there are 3. So that would be, yeah, a decent guess, yeah, for how it goes. Yeah. But don't hold me to it yet. By Thursday, I'll know exactly what it is. In any case, it's not going to be super, super long compared to the midterms. I know I wrote in the announcement yesterday that, yeah, I understand, and I appreciate the amount of time people have taken into doing their midterms. Going through your supporting work, some of it is, like, absolutely beautiful. Like, some of you guys have written better solutions than I could even write on, like, LaTeX. Like, the drawings and the description, I really appreciated how people on that question 8 with the capacitor network, they would literally, like, show arrows about how they, like, manipulated it. I was like, wow, that's awesome. But for the final, you don't need to worry about being that detailed. I mean, you need to show your work so that I understand what you're doing, but hopefully, again, I want you to prioritize getting all the questions done and showing enough work for it. And then if you have extra time in, again, the 6.5 hours you have to take the exam, then you can really start to embellish your work. Some people have literally given me art pieces for their supporting work. It looks amazing. Like, what?
Oh,
yeah. If you all had the same numbers, I would save Albert the trouble and just copy paste, you know, a collection of student submissions. Be like, yeah, that looks great. That looks great. That looks great. That looks great. The issue here with the online thing, though, is that all the numbers are different. So Albert has to slog through and like figure out what the equation is for the answer. That's why it takes a little bit more time for us to write the solutions. Otherwise, if this was a regular quarter class and everyone had the same numbers, I'd have solutions done the second I graded it, and I would just be like, all right, cool, here you go. But yeah, that being said, don't focus on finishing the exam first versus writing up absolute masterpiece Mona Lisa, you know, supporting work for what you did. And another thing is, yes, I know the numbers can be tedious. Believe me, I all the decimals and stuff, I understand that stuff sucks. And some of you guys are already doing this. You want to keep everything algebraic until the very end. You want to try to keep things in terms of variables, and that might mean using subscripts like H1, H2, or like R1, R2. You want to keep that all the way through for a number of reasons. One, it helps reduce any sort of like rounding errors that might happen as you're just like keep putting in numbers to your calculator. Two, you also get to see some cool cancellations that happen. So sometimes like the radiuses will cancel out, or the radii will cancel out, or, you know, the surface area will be twice this surface area, and so it's just a factor of 2. You can't see that if you're using the numbers throughout the whole thing. It's much easier to do cancellations and stuff when everything is just symbolic and algebraic. So that's my word of advice. If you find like the midterms were taking you a lot of time and being tedious, it's good to shift your method of solving these problems and try to do things just in terms of the variables. You want to get comfortable with that now, because when you get to upper division physics, your teacher is not going to care about numbers. It's all algebraic. It's all manipulating variables and stuff. Especially if you get into like quantum. Quantum physics is all wave functions and variables, and they don't really care about numbers. So you want to get good at doing that now. I know numbers are scary, but or numbers are your friend. Sorry, variables are scary. Letters are scary. That's the whole thing. When people get to math and they get to algebra, they're like, wait a minute, I thought math was numbers, not English. Like, why are we doing letters? What are all these letters? Anyways, so yeah. Also, please turn in your exam like in the deadline. Please take the exam in your deadline. Please don't forget to take the exam or say, I had my internet out for 6 hours. Like, do whatever you need to do to make sure that exam gets submitted. Because they're very strict about exceptions. I mean, on midterms, I can be a little forgiving on like you missed your flight or like whatever, because it's 10% of your grade. This is a much higher percentage, and it dictates a lot, and they're pretty strict about what exceptions. Honestly, a lot of times some professors give 0 exceptions, and for instance, if you're sick, you just get an incomplete for the class, and then you got to go take a final again like the next quarter with a different professor, and then they like exchange grades. It's a mess, so don't do it. Do everything you can to try to like take the final during that window and submit it, please. I know with 110 students, I'm sure there's going to be some percentage of a comet comes down from the sky and like does something bad, but yeah, please. Okay. I also released all the clicker questions, the answers, in like a Google document. So if you look on the announcements for today, where is it? Yeah, here we go. Announcements. Yeah, if you go to this like Google Doc, this has all of the clicker questions and what all the answer choices are. And then there's a check mark next to the right one. Okay. The reason why it's copied twice is that's how I dealt with presenting it to you guys. So I would always like screenshot the one without the check mark, and then for my own sanity to make sure Kudu was correct, I would leave the one with the correct check mark on it. So yeah, but they're organized by tabs here, so you can just go to whatever clicker and see what the answers are. So that should help you out instead of having to scrub through all the previous lectures. Yeah, okay. Regrades. Clicker questions. Last homework is due today, 2 p.m. Please try to like submit that, because any sort of extension stuff just delays the final grades, or it makes it a mess and a headache for later. So I want all your grades to be done by 2 p.m. Besides, again, any adjustments to like exams and then the final, that's okay. But it's a really big task for me to go through and take all the clicker questions, all the pre-lecture questions, all the homework questions, and throw them into Brew and Learn. So also don't mind all the emails you might be getting for like the notifications where like assignment has been added. I'm about to add like, I don't know what, probably 40 or 50 assignments. And yeah, also don't email me about errors until I give like the all clear that like everything has been entered, because when I upload things to Brew and Learn, it lags like with the grades, because it has to update it for all 110 students, and then across like 40 or 50 assignments, it can sometimes take hours for it to settle. So I'll let you guys know when I think all the grades have been entered, and at that point you can then email me being like, hey, there's a mistake here, like I did this homework assignment but I don't have credit for it, and I'll make an announcement about that. But yeah, please don't be too concerned about your final grades until I tell you that it's more or less finalized, and then there's always room for us to fix any errors. Okay. Cool. All right, that being said, today I wanted to do a couple review questions, mainly on the first midterm topics. So that includes some fluids, some waves, some what else did we do? Periodic motion. Yeah. So we're gonna do some of that today, and then tomorrow my plan is to do some review on some of midterm 2 topics. So that's gonna be E&M, and then kind of bleeding into some of the newer stuff with like circuits. And then again, the final is Friday. We all say goodbye, you know. And y'all go on with your life, which is awesome. Okay. Cool. All right, let's get into it. Any questions, again, just feel free. Hit him in the chat. I'll answer him. Okay. Let me turn the lo-fi music off. Okay. Welcome to week 6. Last week. Lecture 3, second to last lecture. Oh, this is a gray calculator. We can't have this. Okay, what? Where the hell is this? Yeah, no. No. What? No, sorry. I didn't approve that calculator. No. There we go. That's my calculator. I don't know whose calculator that silver one was. It's not mine. Okay, week 6, lecture 3. Okay, we're gonna start off with kind of a fluids question. I think it's a pretty good one. And then if we have time, I have like an even more detailed fluids question we can go through, but we'll see what we got. All right. Here we go. So, question says, you need to siphon water from a clogged sink. I'm sure this has happened to some of you guys. I mean, the plumbing systems in some of our apartments, especially around LA, are super old, and they just like don't work. No. So sometimes you need to siphon stuff. And this is a cool technique. This is also used to like siphon gas, which nobody should be siphoning gas, but if you need to get liquid out of a container, what you can do is you can use a tube here to like kind of like get it in contact with the liquid here. And then if you apply enough like pressure here to pull this liquid up past this point, and then it starts flowing down this way, it will continue to flow until this is completely gone. Yeah. This is called a siphon, is what it is. It's very cool. And it's a way to move water from like this height out of it, as long as you have the other end of your tube located some distance below it. Gravity will actually pull this fluid all the way down into the pail. You have to give it like an initial pressure, you have to suck on it a little bit initially, an initial pressure, because you need the liquid to clear like this height. But once it clears this height, it's going to want to fall down. And as it falls, because this is a, continuous fluid, right? It doesn't have breaks. It will continue to pull more fluid with it. And that will end up draining this until eventually it's gone. Yeah. Okay. The sink has an area of 0.38 meters squared and is filled to a height of 4 centimeters. Your siphon rises 45 centimeters above the bottom of the sink and then descends 85 centimeters to a pail. The siphon tube has a diameter of 2.3 centimeters. Assuming the water level in the sink has almost zero velocity. Okay. Use Bernoulli's equation to estimate the water velocity when it enters the pail. Okay, cool. So we want to figure out how fast is the water moving as it exits here. Right. Okay, so let's remember Bernoulli's equation, which, here, let me pull it up real quick. Which talks about these three quantities are always constant. All the addition of them is always constant. Okay. Summation. So, right. So, we know that the pressure in a situation is equal to plus 1/2 rho v1 squared. This is the velocity of the water. Plus rho gh1. This is the potential energy due to gravity of the water. This has to be constant. And so, if you calculate this for both situations and set them equal to each other, you can figure out some things. And we say, assuming the water level in the sink has almost zero velocity. So this was done a lot in our previous questions. We usually assume that the velocity of the water at the top here is very small compared to the velocity of the water that's exiting the tube or is exiting the hole in the tank, right? We had, I think there was there's an exam question like this, right? Where we had the water falling out here. And when we do Bernoulli's equation, we don't consider the velocity here, right? We say that this water level is moving down very slow compared to how fast the water is coming out of the hole. And that has to do in part because the surface area of the water coming out here is very small compared to the surface area of this. And I think that's why they give us this here, right? The tube has a diameter of 2.3 centimeters. The sink has probably a much bigger diameter. We could figure that out real quick. If we just want to verify this, we know that, so an area, so we know that 0.38 is equal to pi r squared, right? So then if I go divide that with my gold calculator, not my silver one, 0.38 divided by pi, and then we take the square root of that. And then that's the radius multiplied by 2. That gets us 0.69.
Nice.
Which, yeah, that's a 70 centimeter diameter, right? That's a much larger, cross section than this small little tube. Okay. Let's assume that the pail is empty. Because you can start getting into some weird things here if you start trying to consider, the pressure here, well, how much water is above it, and then how much you got the force of the atmosphere and stuff. So we're gonna make some assumptions here. We're gonna assume that the tube here is we're gonna calculate the velocity at this instant when the tube is right on the surface of the sink. And then when the pail has not been filled at all. Okay. But the opening is here. This diagram is actually kind of confusing. Because notice how they said that the tube rises 45 centimeters above the bottom of the sink. Okay, I see. Yeah. All right, so they're saying this is 45 centimeters. And then descends 85 centimeters to a pail. But they're saying this is 85 centimeters. Oh, man. Why did they do that to us? Okay. The dimensions are like kind of weird here. You just had to use the manual method? No, you can totally use siphons. This works. I mean, again, people use this as kind of like an illegal thing to get gas out of people's cars. They'll put a tube in, they'll suck on it, and you got to make sure the gas doesn't go in your mouth. But then as long as the tube is below where the gas tank is, gas will come out of the tank. Yeah. You just don't want to get like a mouthful of diesel. This is the greedy siphon cup model. It is. It really is. Yeah. Okay. Let me think how I want to do this. Because I wonder if I have to account for the 0.4 here. All right, I'm gonna say that this is here, and this is here. Cool. So let's calculate some stuff. We're gonna call this situation 1. We're gonna call this situation 2. Okay. What's up, Reki? So P1, when we're located. Well, actually, here, I think I have a good idea here. Let's consider that the siphon is not exactly at the surface. Let's consider that the siphon is exactly 4 centimeters, like on the bottom of the sink, because that's the best way to keep draining water, right? If you have it exactly at the surface, the issue is that once the water level drops like any amount, now you're not going to suck up any more water. So in reality, the siphon would be like basically at the ground. Okay. So we can assume that's here. And then here for this 85 centimeters, I think they're assuming that this is also 4 centimeters below at this point. Yeah. Okay. So P1 in this case would be, that's what the pressure is at that point in the tube. That's going to be equal to like P atmosphere plus technically rho G times 0.04 centimeters of water that's above it. Okay. And then we have plus 1/2 rho V1 squared, but we assume that the water level here is not moving very much, so that's going to be 0. Again, that was taken care of here. It says assuming the water level in the sink has almost 0 velocity. And then we have plus rho GH1. Ooh, okay, cool. So we have to come up with they call it, right, like a common datum. We have to come up with like a location for what we're calling height being 0. So I think I'm going to call this, do you see how everything is measured from here? I'm going to call this h equals 0. So in that case, the height of where the tube is, where we're sucking in water, that's going to be negative 45 centimeters. Again, this is similar to what happens in what is it? In mechanics, where as long as you're calling like a certain location, your height equals 0. It doesn't matter where that is, but if you're consistent with everywhere you measure height as also measuring reference to that point, then you're okay. So I'm going to call that height is equal to 0. Okay. Cool. So that's all for situation 1. Okay. So now let's figure out situation 2. Okay. So here, you're still going to have atmospheric pressure, right? Pressing down on that. So that's going to be P atmospheric. That's going to be P1. And then we do have a little bit of, in the solutions here, they say assume that the pail is assume the tube in the pail is about 4 centimeters below the surface of the liquid, so that the pressure at the two tube ends is approximately the same. I see what they're saying. Yeah. So they're saying because this tube is located 4 centimeters underneath a water line and you have P atmospheric, you also want the pressure down here to be the same, which would need to be P atmospheric plus 4 centimeters of water above it. So they're actually assuming there is some water in it, in the pail already. Okay. So we're going to say that's equal, so that's P atmospheric plus rho g times 0.04. Sure. Now this has velocity, right? The water coming out here will have like some velocity to it. And that's what we're solving for. So that's going to be 1/2 rho v2 squared. Okay. And then now we need to come up with a new height. So, okay. Plus rho g. And I think we need to use negative 89 here, honestly. Yeah. Because we're measuring the velocity and everything at this location. Yeah. This shouldn't change. Also, this should not, the rate at which this falls down should not change based on how much water is in here. The velocity should be constant. So, let me see. And this wording is weird. I don't know if I like this question, actually. I picked it because it was one of the last ones, which looks kind of hard. But I think the way they do it is actually wrong. But we're going to do it my way. Okay, so the height here is going to be negative 0.89. The other way we could have done it, if we assumed there was no water in there, then this would have gone away. And then we would assume that the height is just negative 0.85. But yeah, you still have to account for this then. Fascinating. Okay. Okay. So all that's left to do now is solve for V2. So P atmospheric and rho g goes away. Or no, P atmospheric goes away here. P atmospheric goes away here. Yes. Yeah. It is. So then we have rho g, and this is going to be 0.04 minus 0.45 is equal to 1/2 rho v2 squared minus rho g times 0.89. Okay. And all the rows are going to cancel, which is nice. So rho goes away here, rho goes away here, rho goes away here. And then, what do we left to do here? Oh, we're solving for a V2. Okay, so I can add this over. So I have G 0.04 minus 0.45 plus 0.89 is equal to 1/2 V2 squared. Multiply by 2. You're going to get 2G, and then that's going to be... why does the rho g on the 0.04... Oh, it should cancel. Oh, you are right. Sorry. Yes, sorry, I meant to do that. Yep, no, you're right. Thank you, Josh. Yeah. Sorry, I forgot to cancel that one with this one. Yeah, you're right. Okay, so that's 0.44. I think the reason, if the reason I'm a little shaken by this is because I'm verifying this with what the textbook solutions are for this, and they end up having this being 0.40, which is wrong. I'm like, what? And I'm trying to justify like why they do, and they don't, and it doesn't make any sense to me actually. Yeah. So, but that's a fact of life. Sometimes textbooks are wrong. Usually, I hope like textbooks are correct. But yeah, if the siphon is at the bottom, you have 4 centimeters of water above you. You have to keep that. And then this is awful. Like they say this is 85 centimeters, but I have no clue what this distance is. And then in the solutions, they say, oh, we'll assume this is 4 centimeters. I'm like, bro, that's not given anywhere. If I gave this question on a test, hint, I would specify all these things. I really disdain when physics just decides to like leave things out. And they're like, oh, just assume it. I'm like, bro, like, how are you going to get that? Anyways, okay. 2G times 0.44. Let's see what we get. Honestly, the only difference is 4 centimeters, so it might not make a difference. But square root of 2 times 9.8 times. Could you have used Torricelli's law? Torricelli's law? To like approximate it? Maybe. I think there's going to be some weird thing with Torricelli's law based on, like, the position of the siphon. Like, again, where this tube is in the liquid. Square root of 2GH. Yeah, no. And that is Torricelli's law, which is interesting here, right? Because you don't have liquid here, but the siphon does provide a column. Remember in Torricelli's law, we don't actually care, right, about the width of something. Right, so actually maybe the law does work here. So yeah, and that would be correct, right? This would be 44 centimeters. This would be 41 centimeters down compared to 85 centimeters down. Oh, very cool. Yeah, so you would actually get the same thing. That's cool. Yeah, Torricelli's law does work because this column, I guess, behaves as if you have a solid, like, liquid thing here. That's actually pretty cool. Okay. Okay, so square that. So you end up getting 2.93. It does make more sense, but I really like how you thought there, Amelia, because it kind of pokes at how Torricelli's law works, right? She's talking about this. If you have like a tank, and then you have a hole here, and then you have fluid, that the velocity here is just equal to the square root of 2g. I think we say like delta h is what it is, where this is delta h. And again, we don't care like how wide this is. I don't care if it's like lopsided or something. All you care about is the height. And here, that kind of does provide the same thing. You could think of this as a big tank, right? Where there's all this water. And this is the spout. That's actually a really cool way to think of it too as well. It works. No, it's consistent, Amelia. This way it makes more sense, like adding up all the pressures and stuff. But Torricelli's law does work. The only time, again, Torricelli's law does not work, which happened on the first midterm, is you can't have it work when you have fluids of 2 different densities. So if you have multiple densities of fluids on top of each other, you have to account for those. And in that case, you kind of have to do this. Okay. So that's part A. Okay. Estimate how long it'll take to empty the sink. Ignore viscosity. Okay. They're talking about like, so viscosity is kind of like friction for like liquid to like move and stuff. Okay. Well, this is the velocity of the water that is exiting here. Okay. So we can think about the volume, right? So dV dt, so the volume being moved in a unit of time, is equal to the surface area, and then we say like times dx dt. This is kind of also similar to like flux and Gauss's law. So if this is surface area, and then this is the flow rate, dx dt, multiplying this by this gets you the total volume of water that is leaving. And how much water do we need so cool. So the volume that we need to get rid of is the surface area of this times the height of this. And then that is going to be related to the surface area of this times the velocity of this times some time. Okay. Yeah. So total volume. Removed. From the sink is equal to the surface area of the sink times the height of water. And in that case, it had a surface area of 0.38. So that's going to be 0.38 meters squared. And then times the height of the water. Well, there was 4 centimeters of water in your sink. So that's going to be times 0.04. So now if we multiply that together, so 0.38 times 0.04, get 0.0152. And okay, cool. That needs to equal the integral of dV dt from the siphon. Well, actually, sorry, it's integral of VDT. Yeah, VDT. And so that's just going to be the volume, which is the surface area times the velocity. So the surface area of the siphon, that's pi times 0.023 squared. This is like the surface area. And then times the velocity the water was coming out. That was 2.94 meters per second. So this is equal to like meters squared. This is 2.94. This was the velocity. And this is meters per second. And then we multiply by the time to get the total amount of volume that needs to be removed, which is the 0.0152. Okay. So now I can just solve for t here. 0.0152 divided by pi divided by 0.023 squared divided by 2.94 make sure I did this right. Wait. 0.38 times 0.04. That's the 0.0152. Yeah, good. Divided by pi. Oh, this is the diameter, though. Ooh, I screwed up. Sorry. 2.3 centimeters is the diameter. Okay. So this needs to be this over 2. So all we got to do is, sorry, let's go up to here. Divide this by 0.023 divided by 2 squared. Okay, now divide it by 2.94. And that gets us 12.44 seconds. Okay, so time is equal to 12.44 seconds. Nice. Okay. So that's how much time it would take for this siphon to remove all the water from the sink. And we needed to first figure out the velocity coming out of the siphon connected to the sink in order to do that. Okay. Right, okay. Sorry. That's this. Integral of... Let me get this so this is correct. So this is technically correct. This was the velocity, and that equals surface area velocity times time. That's the correct notation for it for the calculus. Okay. Right. Because the change in volume coming through the siphon is the surface area of the siphon times the rate at which that surface area is exiting the siphon, which is the velocity of the water going through the siphon. All right. Does that make sense? It's kind of I hate fluids. I'm going to be straight up with you guys. The things I don't like fluids, and I don't like optics. Because it is confusing to keep track of, like, the heights and the, I don't know, the pressures, and then, like, how much water's above this or something. I'm like, who cares? But they make it as a part of 1B. I would prefer this to be thrown on 1C and just let 1C be a grab bag of fun random topics. In reality, to me, like, physics is mainly like mechanics, E&M, and like quantum. All the other stuff is like little, like, cute little side topics, like thermo and fluids, optics, yeah. But okay. Let's see. That was fluids. Let's do something with... Oh, okay. We can do something with, like, waves. I found this question last night, and I was like, wow, this is actually really relevant. I hope nobody's actually died from this. I don't think so, right? Did y'all get the tsunami warning? Tsunami warning last night? I was like, uh-oh. And then I saw it was apparently like a 1 meter wave. And I'm like, man, we have bigger waves when we go, like, surfing. Like, what? So, but I saw this question. I was like, oh, a tsunami is sort of a pulse or a wave packet consisting of several crests and troughs that become dramatically large as they enter shallow water at the shore. So suppose a tsunami of wavelength 234 kilometers. This is huge. It kind of puts some perspective, right, to, like, how big these waves are in the ocean. And a velocity of 550 kilometers per hour. So it's going really quickly, too. It's like traveling the same speed as I don't know, like an airplane. Travels across the Pacific Ocean. As it approaches Hawaii, people observe an unusual decrease in the sea level in the harbors. Approximately how much time do they have to run to safety? So this is actually an interesting thing they say here. Like, in the absence of knowledge and warning, so if you didn't know there was a tsunami and you didn't know danger was there, people have died during tsunamis because they're attracted to the shore to see the stranded fishes and boats. So yeah, because a tsunami looks like this, right? It has peaks and it has troughs in the water. So you can kind of think of this as like the water, and then this is like flat. And so, especially if you get like closer to shore, right? That that change from like what, let's say this was the base height of the water before a tsunami. They end up seeing the water level drop dramatically, and then like all the boats look like they're in the sand, or, you know, the fishes are just like, yo, where's my water? Where do I go swimming? In reality, there's a massive wave coming here to like fill in that space. So we want to know how much time. How much time do you have? Like, so if you see this, like, if you see this unusual decrease in the sea level, how long do you have until like the big thing hits? Okay, so what we know is that for the amount of distance this wave has to travel, right? That's going to be half a wavelength. Okay, so let's say, for instance, you're looking at like the absolute lowest point here. The absolute highest point is located half a wavelength away. Because it's from a peak to a trough, right? Peak to a peak would be a full wavelength. So this is 1/2 of a wavelength. And that thing is traveling at a speed of 550 kilometers per hour. Okay. So distance is equal to velocity times time. The distance I need this wave to travel is 1/2 of a wavelength. The velocity at which it's traveling is 550 kilometers per hour. So we can just say like 550 kilometers per hour. And then I think you can just solve for the time here. It's actually not, this is actually not a hard question, but a relevant one to today's news. So 1/2, and then the wavelength, right, we said was 235 kilometers. Okay. So we just divide by 2, divide by 250. So 235 divided by 2 divided by 550. We get that in hours. Okay, remember that's in hours. But 0.2 of an hour doesn't really tell me much. So then I just multiply that by 60 to get minutes. 12.8 minutes. Wow, the first thing I see when I join in after a final is doomsday. I know. So t equals 0.21 hours, which you multiply by 60 minutes in 1 hour. And so that's equal to about 13 minutes. Okay. So good to know, right? If you see the shore get really thin all of a sudden, you got about 13 minutes before the big thing is going to hit. Yeah, so this is just VT. Yeah, nothing really crazy here. We could, for instance, we could find the frequency of this wave, right? So we know that lambda f is equal to v, right? So in this case, 235 times f is equal to 550. And that's over hours, right? So 550 over 235. Assuming I can outrun nature. Yeah, that divided by 235. So that's 1 over hours. So we have f is equal to 2.34 hours to the -1. But usually we want this in hertz. So what would I say is like 1 hour is 3,600 seconds. Okay, so then we would divide that. And you get something much smaller, yeah. So 6.5 times 10 to the -4 micro, times 10 to the -4 hertz. So we didn't need to convert to meters. In this case, you didn't because the wavelength was in kilometers and the velocity was in kilometers per hour. Where did this question come from? Doesn't seem like Kudu could be this on point for predicting natural events. It's from a physics textbook. It's an old one. But I like it. It's a good physics textbook. Yeah. I just thought that was funny. I was going through like some of their old homework questions and I saw something about a tsunami and I was like, oh, wow. That's literally what's happening right now, tonight. So I put it on there. That's something to go through. But yeah, this isn't too hard. I think mainly the difficult thing was realizing that the distance is from a peak to a trough, which is then half a wavelength. Yeah. Okay. On the subject of waves, that was just kind of a fun one. It's pretty easy. Let's talk about this one. which I think was similar. Remember that tsunami movie where the water levels of Santa Monica Pier just went down? Yeah. Well, apparently you got 13 minutes, man, to get out. Okay. A mass attached to an end of a spring is stretched a distance x naught. Okay, so let's see this. So, from equilibrium. So let's say this is x equals 0. And the thing stretched out to here. And then it's released. At what distance from equilibrium will it have velocity equal to half of its maximum velocity? Ooh, very cool. So we want to know x equals what when v is equal to 1/2 v max. Okay. So let's think about with springs. This is kind of a mechanics thing. You did springs in mechanics. I'm sure you did, yeah. But at this point, this has potential energy due to a spring, which is equal to 1/2 k x naught squared, and it has kinetic energy equal to 0. Oh no, Claire! You're in Hawaii right now and we had to evacuate and sleep in cars? That sucks. I saw some video. Yeah, I have my one of my family members, partner, girlfriend, whatever you call it, is in Hawaii. And they said they didn't see anything. They said it was just kind of like a little like a little tide pool. But I hope you're safe if you're in Hawaii. I didn't see anything on the news. When I was thinking about like posting the tsunami question, I was like, I need to wait till the morning to see if this was a disaster or not before I actually post it. I don't want to trigger anybody. But I think it was okay. Sounds like it was all right. But that must be crazy. I saw videos of people like cheering in the hotels as I guess the time was hitting that the tsunami should have been hitting. But I don't think it was anything more than like a meter. It's crazy that they made all the boats leave though, right? They forced all the boats in the harbor to like go out. If it was a disaster, you can turn it into a fluid dynamics question. Uh-oh. Yeah, unfortunately. Oh man. Force analysis and pressure. Yeah, we could. Yeah, the amount of force. Dude, water is crazy. Like it's a very powerful force, honestly. There's a lot of weight in water. People don't think, I don't know if I surf a lot, and sometimes when you get hit with a big wave, you get like held down for like a significant amount of time. It like pushes you down. Like it'll push your face like into like the sand on the ground and be like, no, you're not getting up. And I'm like, okay, I'll wait. Yes. Okay, so here kinetic energy is equal to 0. We know, right, that as this object here moves back towards the equilibrium, the potential energy of the spring will go down, and the kinetic energy will go up. And so we can say here, at x is equal to x naught, we know that mu s is equal to 0, but ke, which is equal to 1/2 mv squared, will be maximized. And since this total energy has to equal this total energy, that will have to equal 1/2 k x naught squared. Okay, so then we can kind of get some cool stuff here, right? So cancel this, cancel this. We still got mass in there. So we get that V max squared is equal to k x naught squared over m. Okay. Okay. So, and we want to figure out when V is equal to 1/2 V max. Oh, okay. So let's do this. Okay. So now we have this situation. Or let's not use purple. Use a different color. Let's do this. Okay. So when V is equal to 1/2 V max, okay, then you know you have some spring potential energy, right? That'll be equal to 1/2 k. Let's just call that x squared because I'm looking for whatever that x is. And the kinetic energy will be equal to 1/2 m, and we want it to be 1/2 Vmax squared. So 1/2 m, and then that's going to be 1/2 Vmax squared. Okay, so that's going to pull out a quarter, which is then going to pull out like an eighth. So that's 1/8 m Vmax squared, if I distribute the squaring. And then Vmax squared is just this. So we have this, goes into here. So 1/8 m, and then that's going to be k x naught squared over m. Is going to be the kinetic energy. And then we know that mu s plus ke is constant. And in this case must always equal one of these totals. This total is kind of the easier one to deal with, because we know it was held out at rest at this position, right? So we're using this like total. Okay. So if we add these together, I'm going to get 1/2 kx squared from here, plus the m's are going to cancel, so I get plus 1/8 kx naught squared. Right? Yeah, okay. Is equal to 1/2 kx naught squared. Ooh, okay. So when we're solving for x, right, we're trying to find this position. So 1/2 minus 1/8 is 3/8. So if I move this over, guys, I'm going to get 1/2 kx squared is equal to 4/8 minus 1/8 is 3/8 kx naught squared. K's are going to cancel. And then I can cancel out one of the 2's here, make this like a 4. And so now we're left with x squared is equal to 3/4 x naught squared. So then x is equal to the square root of 3 over 2 x naught. Cool. So this is the position. So when it's square root of 3 over 2 times the initial stretch, that's when the velocity is half its maximum velocity. That's a cool one. Yeah. Okay, and then the other thing we can do here is like its acceleration is equal to half its maximum acceleration. Ah. So maximum acceleration, that occurs when the net force on the object is maximum. Okay, so A max is when, because by F equals ma, is when F max is occurring. And let's remember that the force on a spring is equal to negative k x naught, negative kx. And so when this is the biggest, you're going to have the biggest force, which means you're going to have the biggest acceleration in the opposite direction of the force. Oh, interesting. You could do it that way. Vmax is omega a. A max is omega squared, negative omega squared a. Okay. That's another way. Let me see if we can use that next sib. Let me see if I can use that. I was going to do it the traditional way here. So we know A max occurs when x is equal to x naught. And so they wanted to know when the acceleration is equal to half its maximum acceleration. Oh, well, look at this. Acceleration is equal to f over m. And then f is equal to kx, right, over m. Or it's negative kx technically, but whatever. We're talking about the magnitude of it. So a is linearly proportional with x. So the higher you have x, the higher you have a. So if you want half the maximum acceleration, you need half the maximum displacement. Ah, okay. So we say x is just equal to x naught over 2. then A is equal to A max over 2. And that kind of comes from this. So, again, like A is equal to negative K x over M. And then there's a linear relationship between it. Acceleration is equal to half. Okay. So, if you have A equals A naught, or A max, over 2. Okay, watch this. This is actually kind of cool. So you can say that A max is equal to negative K. These are constants, right? And then this would be X max. And so divide by 2, divide by 2. You see that A max over 2 occurs when X is X max over 2. What about the other way to do it with K over... So, yeah, from this, right, V max is equal to omega A. And omega is equal to the square root of K over M, I believe. Yeah. Could you have done it this way? Yeah, without the negative? Oh, it's okay. I mean, yeah, I don't really care about the negative. I think we're talking about, like, the magnitude of it. Yeah, the issue is that this doesn't have anything to do with distance, though. That's the only problem, Sibley. So when you have A max is equal to omega squared A, that's equal to K over M A. So you're trying to figure out when A is equal to... Oh, and A is the amplitude. Sorry, right? This is X naught. This is X naught. Yeah, so I see what you're saying. A stands for amplitude. And this comes from the sine and cosine definition of harmonic motion. So this is X naught. There you go. That's what you want. Uh-huh. And you see how that's kind of the Kx over M? Yeah. Yeah. And that's actually where this expression comes from, right? Yeah. So A is equal to Km. And if we want to say like A over... like a proportion of A max. So like 1/2 A max is then equal to K over M times 1/2 X naught. Okay. Cool. And then this, yeah, this whole thing here is like X. And then this whole thing here is now A. Okay. Yeah, and A equals K over M times X. Very cool. And this is all like kind of going around in circles. But F equals MA. So that's why these two things, which also is equal to KX with a minus sign. Okay. Bunch of different ways to solve that. But yeah, the answer is X naught over 2. Cool. Yeah, that's another cool way to do it, Sibley. You know, physics is all like self-consistent. All right, let's see if we can do this one real quick. Doppler flow meter uses ultrasound waves to measure the blood flow speeds. Suppose a device emits a sound at 3.5 megahertz. What is the speed of sound in human tissue? And that the speed of sound in human tissue is about 1540 meters per second. What is the expected beat frequency if blood is flowing in large leg arteries at 3 centimeters per second away from the sound source? Oh, this is cool. So here you have your ultrasound, which we're going to say is the source. And that's emitting waves towards blood, which at this point is going to be the observer. Okay? And we know that it's moving away at V is equal to 0.03 meters per second. Okay. So the ultrasound waves are going to travel this way, and because there's a difference like in their velocities, this is going to hear this at a different frequency, a shifted frequency. So we could say that here, F0 is equal to 3.5 times 10 to the 6 hertz. But then over here, this is going to hear it at some F1, some new frequency, which is going to be equal to the initial frequency. And then you got to remember the Doppler shift equation. I forget if it's observer over source. One sec. Doppler shift equation. It's observer over source. Okay. So V plus VO, and then V plus VS, but then we're going to change the signs based on things. So the source is not moving. Right? Source is staying still, so that is 0. And then because we're moving away, I need the frequency to go down. I need to hear, as an observer, I'm like trying to run away from the sound. So I'm going to hear a lower frequency. So that's going to be V minus V naught. Okay. So I think we can kind of just leave this as variables for now. Let's just leave it. We're going to say V naught, F naught, and then V, in this case, this is V observer. We're going to say that V is this. This is the speed of the sound in whatever the medium is. In this case, it's human tissue. Okay, so we're going to say F naught, V minus V naught. We're going to leave it like that. Okay. Now, the blood is the source. It's still moving 0.03 meters per second, but it's emitting sound towards the ultrasound device, which is now the observer. And it's going to hear some new frequency, F2. And whatever this is emitting, right, that's the same F1. So now F2 is going to be equal to F1, V minus of the observer. Well, the observer speed at this point is 0. Oh, sorry. Yeah, this is over V. Thank you. Good catch, Amelia. Yeah, that would be divided by 0. That would be really bad. Sorry, this is divided by V. Sorry. This goes away is what I meant. Thank you. This is V plus 0 because the observer is not moving. And now the source is moving away, so we should hear a higher frequency. So this should be V plus V source. Oh, sorry, we should hear a lower frequency, which means I need a higher denominator. Okay, and that's what we're left with there. Cool. So then that's F2. So then F2 is equal to whatever my F1 thing was, which was this. And then it's times V over V plus V source. And V source and V observer are the same thing. They're both 0.03 meters per second. Okay. But then what we're trying to calculate is the beat frequency. So let's remember that beat frequency, that's going to be the difference in frequency between what you emitted and what you heard back. So that's going to be equal to F0 minus F2. Okay. So looking here, right, I already have an expression for F2. So I can say, okay, cool. So F0 minus this, that should be equal to my beat frequency. And now all that's left to do is to plug in some numbers, right? Because F0 was equal to 3.5 times 10 to the 6. V was equal to the speed in the tissue, 1540. And then we say VO equals VS, which is equal to 0.03, I think, yeah. And this is what I talk about on like an exam. You want to just get down to the variables here. Don't start plugging numbers in until the very end. You like this stuff? This stuff is kind of cool, yeah, right? Okay. So I could have simplified this further actually by pulling out an F naught and then doing 1 minus, but I'm just going to leave it for now. So 3.5 e to the 6 minus 3.5 e to the 6 times 1540 minus 0.03. But then we got to divide this. You got to get careful with all your parentheses. And there are faster ways to do this with simplifying. I probably could have. I could have made that like 1 minus V naught over V. And then this is going to be 1540 divided by 1540 plus 0.03. Okay, cool. And so that gets us 136.36 hertz. Which, ooh, look, so we can see from, I always like seeing what like the solutions manual does. They did a little bit more of the math cancellation, but they also got the same answer. 136.36, cool. 140, nice, we did it.
That's dope.
I love getting the right. I love getting the right answer. It's a nice little self-esteem boost, I guess. I'm like, wow, nice. Physics is not a lie. Okay, cool. All right, that's all I wanted to go over today for again, some fluids, some sound, some waves, pretty good questions I could put on the exam in some shape or form. So make sure you understand this stuff. If you don't, come by office hours. I'll have office hours today at 5 p.m. Pacific. So that's going to be in about 3 hours. And then, yeah, come by tomorrow for the last and final class or lecture of the quarter. And we're going to be going over a lot of like E&M and circuit stuff to just review. So, cool. All right. Enjoy your Wednesday. Yes, enjoy your Wednesday. I will see you guys later today at office hours, or I'll see you tomorrow. Peace.